the minor related to technical complication. It's a great pleasure to introduce H.Spohn, who will talk about the hydrodynamic equations for integrable systems, the case of the classical Toda lattice.
Thank you very much, Robert. I'm very happy, after so many years of planning the research stations, now I see this in action, at least from a distance. And so, I'm very happy that we have now the Center for Mathematical Physics where we can have our conferences. So as you can read, my title sort of, I believe at least, falls into the sort of main title of the program. The emergent equations are the hydrodynamic equations, which of course I will explain. And the underlying systems are many particle systems, but they are of a very special type. They are integrable many particle system, which means that rather than having a few locally conserved fields, there are many of them. And one of the tasks of the talk will be to explain you what happens in such somewhat, sort of singular cases. Now, this means that, you have to very fine tune the system. So in particular, it means that there are apparently no really good examples in higher dimensions. So, the system will be actually one-dimensional and the interaction will be very, very special. But otherwise, it's a very interesting structure. Roland Dobrushin many years ago, in the mid-80s, he was very, very fond of this topic and worked on this for years, also together with Poltrigini and others. But then, this somehow was sort of a more probabilistic activity and was not so paid too much attention by the physicists. But in condensed matter, it's sort of like maybe 5 years ago, somehow they realized, how useful it would be to have a hydrodynamic description. And since then, there have just been plenty of papers. Very, very good young people and, lots of interesting results. So I will not give a survey. This sort of, particular for this audience, but in general, I think this would be not a very good idea because, you wouldn't know where to start and to end. Rather, what I want to do is I would like to explain you this very specific structure in the case of a system which, I personally understand best, but also in general, compared to other systems, it's sort of the prime example where you can see the mathematical structure. Now, I should warn you, yesterday, we had sort of lots of explanations, and at the end of the explanations, there was a big theorem. I have no big theorem to report. As I go along, you will see that there are all kinds of interesting mathematical avenues which one can pursue, and which hopefully will be done in the future. The main point is try to, get you an understanding why this particular type of equations very naturally appear in any many-body integrable system. Specific case I study is the Toda lattice. And so let me start with giving you the underlying microscopic system. So it's classical mechanics. So I need very little notation, and I think many things can be just explained by word. And so let me just sort of remind you. This goes back to Toda. He of course knew about soliton solutions for nonlinear wave equations, and he was curious whether similar kind of things could be happening on the lattice. As one knows, for harmonic systems, you can write on harmonic systems in the continuum. The free wave equation, and you can do the same thing on the lattice. And of course, they have rather similar properties. And what he discovered is that there's a very specific choice, namely, you take the usual particles with kinetic energy. So these are classical particles, kinetic energy, and momentum Pj, and they have positions Qj, which at the moment there's no constraint. They are just living on R. And the interaction is sort of like what we call the chain, in the sense that it's not a permutation. We are in interaction like a real one-dimensional fluid, but you have to label the particles, and then you get an interaction between neighboring indices. And this interaction happens to be the exponential function. So what I want to say is that if I replace this exponential function by some other function, you will have totally different dynamical properties, and the kind of things which, of course, I'm telling you cannot be used whatsoever. Okay, so here I've written down Newton's equation of motion. I mentioned already there are sort of no free parameters. You can sometimes find here some decay constant, but this can be all scaled away. So this is the system which I'm going to look at. Okay, now the other models, you can take the classical vector freeze equation in one dimension, Sine-Gordon. Yesterday we had a lot on the nonlinear Schrödinger equation. The nonlinear Schrödinger equation is actually an integrable system in one dimension, so it would also fall into this general scheme. You have XXC models, you have the famous linear delta Bose gas, which is particularly interesting because it can be realized experimentally, and so the predictions which come from hydrodynamics can actually sort of check against experiments. There is a Fermi-Hubbard model, there's a quantum Toda, that's just the quantized version of that one, etc., etc. So, it's not just a single system, there are many, but as I said, I will focus on this one. Okay, so we have particles on R, so the natural way to think about it would be to think of a fluid. I mean, so these are just particles moving on the V line. But, as written and also in terms of how Toda was thinking about it, you can also think of this as sort of like a discretized nonlinear wave equation. If I sort of take a totally naive continuum limit by replacing differences by derivatives, then you see that it's really a nonlinear wave equation with a rather funny type of interaction where this capital F is given by the exponential function. I don't think this continuum equation has been ever sort of studied. People are more interested to, taking limits and then getting quarter-vector freeze or other one of the more known examples. Okay, so then the next thing I would like to sort of give you a little picture of how these particles move, and then sort of brings me to another point which is very important for this hydrodynamic limit. Namely, so here I put 6 particles on a ring, on a circle, and here they are moving. So this direction is the time, and I have 6 particles which are started at some particular random type initial condition. And the thing which I want to emphasize is, you see, there's a lot of work on scattering theory. Of course, these particles repel with this exponential potential, and if I wait long enough, they just sort of separate and then just move like free particles. And of course, this is the same if I go to plus infinity and to minus infinity. Still, I mean, Jürgen Moses studied this problem. It's an interesting problem, and people have sort of, did all kind of variations on this. But this is totally useless for hydrodynamics. I mean, you see, it's like a real fluid. I mean, you want to have the fluid sitting in a container. If I remove the container and the particles are expanding, out in empty space, that's a totally different physics situation. And so I emphasize that we want to be on the particle, and now, of course, things go on, and you see here you get sort of a nice 2-particle collision. So this is sort of 2 isolated particles coming with rather definite velocities, and then they sort of do the typical 2-body scattering. Here's another one, but then you have lots of sequential sort of scatterings which cannot be sort of separated into 2-body interactions. So it's a strongly interacting system. There's no small parameter. It's not a low density regime whatsoever. Okay, so that's what we want to understand. Now, if I confine the system, then of course you can ask yourself what happens, for instance, in the long time limit, and there will be presumably a non-trivial time stationary measure, and all kinds of things which you know from statistical mechanics. So this somehow we have to develop. Okay, so now let's see how I want to proceed. So the way I want to proceed is I simply assume that not everybody is familiar with hydrodynamics, and so I want to make a little detour by telling you what would be happening in. So this I call hydrodynamics 1 for a standard simple fluid. I mean, so this would be now particles on the real line, let's say, with some short-range interaction. And in this case, generically, you will have only 3 conservation laws. So which is the mass, and then there's, of course, the momentum, because the interaction is translation invariant, and then there is the energy. And now the idea is that we start with sort of reasonable initial data, which, however, have the property that if I look locally, then it looks like one of the thermal equilibrium states. And I'll come to the formula in a sec. But when I'm then sort of on a macroscopic scale here, I see sort of like the density maybe or inverse temperature. I see this as a smoothly varying function in space and time. But when I freeze, and then I just ask myself, what would be the particles is there some law for the position and momentum of the particles very close to this macroscopic point? Then the assertion is yes, there is. Namely, it will look like a quant-canonical equilibrium measure. And it's quant-canonical because, you know, we look at the small subsystem, therefore typically also the number of particles will fluctuate. And so this local equilibrium will be then characterized by three parameters because I have three locally conserved fields. And we know how to write down the quant-canonical measure. I mean, this is sort of what Gibbs told us. And I only want to emphasize one important structure, namely in the quant-canonical prescription. What you do is you basically take a linear combination of the conserved quantities. This is the energy, this is the number, and that's the momentum. And each one of them sort of carries a label. Of course, you know, some of them are physically very accessible and have their own names, but mathematically, you just think of some linear combination, which of course is also conserved. And then, but the important point is that you know, up here in this exponential, you should include all of them. I mean, you know, very often one forgets about the mean velocity because Galilean invariant. But if you want to do hydrodynamics, I mean, that is another conserved quantity. And so I really have three parameters, not only one, three. Okay, and then what you want to do is sort of rather simple, namely, you would like to sort of compute the average currents, which you can sort of write down something in terms of the mechanics of your system. And you want to, so you do the average with respect to this thing. So it's some function of these three parameters. And you want to express the average currents in terms of the average fields. That's sort of, you know, a functional relation. It's here just a function of three parameters, so R3 to R3, which you want to compute. And this is a computation which you do in equilibrium. There's no dynamics whatsoever. It's a purely equilibrium statistical mechanics. Well, if I have solved task one, then you just say, okay, I mean, you know, let's assume that initially I have a slow variation of these parameters. I mean, just like in this picture in space. And then the claim is that this kind of local equilibrium persists in time. And I will see then a slow variation both in space and time. It will be to first order will be ballistically, so you know, x and t are of the same order, and then, but then you know, most amazingly, I mean, there is a closed set of equations which are, you know, the equations which somehow Euler sort of discovered purely phenomenologically already many sort of some centuries back. Okay, so of course, eventually you want to write down the evolution equation, not in terms of these funny parameters, but in terms of the field averages. But that's a sort of a small detail. So this is the task number 2. Now, task number 2 is difficult. In fact, it's very difficult, and we have no idea how to do this. Of course, people have tried. I mean, when you look in the literature, there are attempts. But you know, the punchline is that, you know, to understand, you know, even in one dimension, this kind of chaotic dynamics seems to be a totally hopeless task. So the task 2, nobody knows how to do. Now, the same thing will be true actually for the so this is just what I repeat here. The same thing will be actually true for the integrable system. There you might think that maybe this dynamical issue could be resolved. But for the purpose of the talk, as you will see, you know, all what I'm trying to do is I'm just trying to solve this problem here, namely the average currents as a functional of the average fields. That's the only thing which I will address during this talk. Now, once I have this functional relationship, and then, you know, with the same confidence as for a small number of degrees of freedom, a few number of conserved quantities, I can write down the Euler equations, and you know, so mathematical proofs have to wait for some time later. So here is the program for hydrodynamics 2, which is integrable systems. And you see, it's a guess at that moment. I mean, you know, the claim that the same procedure which worked so well in the non-integrable case with a few conserved quantities should, in fact, work also in this much more general setting. Okay? So I put here the same strategy as for simple fluids. That's a pure guess. But now we have 5 years of rather intensive work and a lot of comparison, in particular also comparison with numerical simulations of various types. And the overall feature is that in this community, you know, I mean, they are absolutely convinced that, you know, this simple picture of a hydrodynamic scale actually also applies to this somewhat sort of outlandish integrable systems. Okay. So what we have to do is we have to then first understand what we mean by average. That's not at all obvious. You will see in a second. But once we know what we mean by average, then I have to compute the average fields. And when I know the average, I can also compute the average currents, and hopefully I can make this interconnection. Okay, so now we have to just work a little bit and see how we can do it. And the first thing is, I told already that we want to confine the system. So this is by imposing periodic boundary conditions. So you give your first a cell, let's say of size L, and then you put some particles, and then you just repeat them periodically. Or if you prefer, I mean, you can also put this boundary condition. I emphasize that, in the literature, very often people say, periodic boundary conditions, and they put L equal to 0. That's a rather unphysical way of thinking about it, because L is the parameter which controls the density of the particles or the interparticle distance. And that's, of course, a very important physical parameter which you cannot leave out. I mean, it's the one which we can see with our naked eyes, whether the particles are closely spaced or not closely spaced, and we better keep this into our hydrodynamic description. Okay, so now we have set up the system. I'm on this ring, and then now we just solve the equations of motion. But in fact, what we want to know is actually what are the conserved quantities, right? I mean, that's really the dynamical information which we want. And just staring at this little formula and equations of motion doesn't help you so much. But fortunately, this is something which was done many years ago. This was done around 1974. Sort of 6 years after Toda proposed the system, and Flaschka was at the time at the Courant Institute. Lex was around, this was the high time when people understood a lot of structures of integrable PDEs. And so, he was just at the right location. And so what Flaschka did is he said, well, okay, let's rewrite the system in a slightly different way by introducing these wedges. I mean, that's just a positional difference between neighboring indices. But this is somewhat trivial transformation, but let's make a nonlinear transformation by taking the exponential of this with the 1/2. Okay, so this wedge has no constraint. It can have either sign, but the HA, of course, must be positive because it's exponential of a real number. Okay, and now we can rewrite the equations of motion in terms of these new variables. And now you see, you lose a little bit the physical intuition, but now it looks sort of already pretty algebraic. I mean, the nonlinearity is sort of just quadratic, and then you see, some independent terms, and then you see a coupling to the right neighbor, and then you see a coupling to the left neighbor. So now we are really, we have a real sort of lattice field theory. So let me just, for the future, let me just think about as a lattice field theory. I mean, and then, if you want to compute some physical observables, maybe you have to do some mapping. But let's think about a lattice field theory. So we have n sides now. At each lattice side, I have these variables, the q's and the a's. And for them, when you go back, I mean, you see that you can just impose the standard periodic boundary conditions. The phase space is R for the momenta and R plus for this for the Flaschka variables, the A. And so we have a nice lattice field theory. Okay. Now we want to look at conserved quantities. Now, conserved quantities are simply functions on phase space. It's a big phase space function on phase space which do not change in time. Maybe for a classical system, this is good enough. For a quantum system, this is of course very stupid because there are just too many such objects which are not changing under time. Any projection onto an eigenvector of the Hamiltonian will not change in time. So that's not a very good quantity. So in fact, we are asking a somewhat more restricted question. Namely, we want to have a function which is locally conserved. Okay, and since this is such an important notion, let me just explain this to you in the simplest case. And it's this condition which will throw out all strange things like highly non-local functions which are not part of the hydrodynamic picture and are simply not covered by that kind of sort of emergent theory. So here is what you check. I mean, it's a simple algebra that the Rj is simply the log of A, and therefore you see when I put the log of A here, you have a telescoping sum, and so that's certainly conserved. So this sum is conserved. So the sum over the Rj is a function on phase space which is conserved, but it's a very special function because it's just a one-point function. It just depends on the single lattice side. If I take the time derivative, it's equal to 0. But because it just depends on the lattice side, I have actually, it's a field which has a density. The field is a global function. depends on all variables, but the density just depends on a single lattice size. So this is what I mean by local. Of course, it could be some other function, Rj times Pj plus 1. That would be another local function, right? But it's important that it's local. And then, you know, once it's local, the Hamiltonian is local, there must be a current which is also local. Now here I can compute this derivative very easily. And what you find is just, you know, the difference in position. So this is sort of like mass conservation. I mean, you know, change its mass is sort of like the momentum, derivative of the momentum. And then now you see that it's really a lattice derivative. So it's such kind of things which I call local conservation law. And of course, you know, the local conservation has the property that when I look now at the sum over these shades in some bounded interval, then it will change only through the boundary. Okay, so I made many words about this, but I think it's physically a very important restriction, and also mathematically, if we are starting to look for non-local conservation laws, then, you know, who knows what we are looking at. But the local is sort of the one which is very crucial. Okay, so comes the question: what are the local conservation laws? Okay, and fortunately, Flaschka actually was telling us how to do that. And so let me just sort of briefly remind you of what he discovered. So he said, well, okay, let's simply organize these dynamical variables in a matrix, which is called the Lax matrix. And we do it in such a way that the momentums are along diagonal, the Flaschka variables are along the off diagonal. Because we have periodic boundary conditions, we put an AN up here. So you see a nice matrix. It's obviously a symmetric matrix. It has real eigenvalues. And then there's a companion matrix which has no name. Sometimes people call about the Lax pair, but then, you know, who's the other side of the pair anyway? So it's just sort of mathematically, it's very easy to say. I mean, along the diagonal, you put 0, and here you put the same, but you put a minus sign. So Bn is an anti-Hermitian or anti-symmetric matrix. Okay, all these things will evolve in time. So all the coefficients are actually time dependent, right? But here in this notation, it's suppressed. And now what Flaschka discovered is that the equations of motion can be written in a very simple way. Namely, if I look at the time derivative of this Lax matrix L, it's just a commutator with the Bn. But the Bn, you know, generates sort of a 2-parameter unitary group, and therefore you know, it's isospectral. It preserves the eigenvalues of Ln. And so simply from this equation, you discover that you have found very easily the eigenvalues. I mean, maybe not explicitly, but, you know, a very precise and concrete mathematical prescription. All what you have to do is you solve the eigenvalue problem, and you think of the lambdas as some complicated function of all these entries, and these are conserved quantities. They are not changing in time, but they are not local. Why are they not local? Well, because these are eigenvalues of such a matrix. And if I start changing the little a over here, of course, you know, this lambda j will go all over the place. So they are certainly not local. But Flaschka, you know, of course, they understood these things very well. I mean, I'm just sort of repeating what people know. So he realized that, of course, there's a very simple prescription how to get local versions. All what you have to do is to take the trace, the nth power, the trace of the nth power of the Lax matrix. Well, then if you write out the trace, I mean, that's sort of, you know, sum over the diagonal, and that looks already like a density. So presumably this is the density of the QA, and the QAN is conserved because, you know, the eigenvalues are conserved. But now you look at this more carefully, and, you know, it's a tridiagonal matrix. So such powers can be written in terms of a sum over random walks. And since it's, you know, an important tool, and also, you know, that I not just keep going on and on without having you a chance to sort of think about it a little bit. If you expand this, you see then, because it's a tridiagonal matrix, it will be a random walk which has either go straight up or down. Okay, and if I want to do the JJ matrix elements, I have to go, let's say I do n's, want to look at the conserved field number n, then I have to do 6 steps from 0 all the way up to n. And I have to start here and end up at this point. And then you see one path would be something like this. So this goes up, go up. So this carries a A0, and another A0, that's A0 squared. Then you have the diagonal pieces which carry a momentum. So this is P1 squared, and this one is the A1 squared. So this particular random walk corresponds to this mononomial. But now I have to take the sum over them. And then you see you get some complicated polynomial, which of course, you know, writing out explicitly is sort of no use. The thing which I want to emphasize is that it's a finite sum, because I have a finite sum of random walks. And therefore, I found indeed a function which is local. You see, so A0, P1 squared, A1 squared, that's the local function. All right, and so you see that what Flaschka sort of understood, and what he gave to us is a rather concrete formula for the locally conserved quantities. Now, of course, we also want to do the carbon. I actually prepared the talk by showing you a slide on this, so let me sort of spend no time on this, and maybe, you know, I can come back to this. All right, so now we have the carbons, and now, you know, the question is, what do we want to know? Well, I mean, so I mentioned already the long time limit. The long time limit in this case, we know actually, it's a very beautiful piece of work by Henrici and Kappeler. Kappeler is actually in Zurich in dynamical systems. And now you just do you know, integrable systems of classical systems. So you know that these things are moving on invariant torides, but typically with frequencies which are non-commensurate. And these people, they control sufficiently well how the Hamiltonian is expressed in terms of action variables, and they make sure that there are no flat pieces. I mean, that's sort of the crucial condition, but this they actually prove. And therefore, we know that in the limit time t going to infinity, we will go to the uniform measure on the tori. Now, you know, which tori, I mean, this depends on the initial condition, but once I tell you what the initial action variables are, then on that particular tori, I get the uniform measure. So now we can do microcanonical statistical mechanics by just sort of computing, you know, in the appropriate sort of, we have some sense we have to compute, you know, the volume of this torus, and that I don't know how to do. Nobody knows. I mean, maybe it can be done. I mean, I just have no idea how to do it, right? I mean, so you see, if I want to do statistical mechanics in the microcanonical prescription, I'm not sure what to do. So, well, let's proceed anyhow, and let's say presumably there's some sort of equivalence of ensemble. So that's one of the mathematical problems which you might want to study. And so let me just do it for the case which you know already. This is a conserved stretch. I mean, the sum over the RJs. And now I put this already extensively, so it's n times L. And now I just replace this by the exponential, so I get the product over these things. So this is much nicer than this one. And the assertion is that when I look at the large system and then look at local observables, then in that limit, I mean, you know, these two measures are actually the same, provided I connect the L and the P in the right way. Now, why is this important? Well, because you see the interaction potential was this decaying exponential, but now from this constraint, I get another part of the potential, which is simply increasing. Of course, this pressure P is physically the pressure. I mean, how much I press the system from outside. This must be positive, and so this has actually increasing slope. And now you see that we have a stable system. I mean, it goes to the interaction potential goes to plus infinity for minus R and plus infinity to plus R. And so, you know, this simple confinement written in the grand canonical language gives you the appropriate confining potential. So now we have already the a priori measure. So this is of the analog of the Lebesgue. And because we did this small change of variables, I pick out now, this is just this term written in the A variables. But here I get a little extra factor because we did this change of volume element. And of course, this a priori measure is invariant under the Toda flow. Okay. So what about the Gibbs meshes? You see, it's just like in ordinary statistical mechanics, you have to give now a weight. I mean, so this is just the a priori, like the back, and then you have to put the weight. And now you say, you know, I know already e to the minus beta h. No, that's sort of course, not incorrect, but it's of course not correct, because the rules of statistical mechanics tells you that you have to consider all conservation laws. You cannot just sort of single out 3 of them. If you want to do hydrodynamics, you need all. And that's what we have to do as a next step. Okay, so here's my Boltzmann weight. It's the exponential of a linear combination of this of the traces of the Lax matrix. Okay, now we do just sort of, you know, functional calculus with matrices, and then you can sort of put this under the trace, and you see what you have to do is that you have to, the Boltzmann weight can be written as a trace of some function of this Lax matrix. Okay, now some function we don't know. I mean, but you know, if you look at the lowest orders, the simplest function here should be confining actually, so it's stable. So the simplest function would be quadratic. This corresponds to thermal equilibrium. That's a particular simple case. But then the next one would be to put here the quartic term, and so maybe you have a function like this, or maybe you have some higher order polynomial, you know, the exact class of functions which we can allow, that's actually, there's a very nice paper by Alice Gouinet. I mean, sort of, you know, we talk to each other and see somehow analyze some of these questions, but you know, it goes too much into details. The main point is that I want to have this function confining, so it must increase at infinity. Otherwise, you cannot normalize. You know, with respect to the free mesh, you cannot normalize. And so you get an object which in the physics literature is called generalized Gibbs ensemble. I mean, mathematical physicists didn't like that name so much because, you know, the idea of looking at general Gibbs ensembles, so it goes all the back to the grandfathers of the subject. I mean, that's clear. But here, this is not what is meant by generalized. Generalized means I give you some Hamiltonian system. I look at all the locally conserved quantities, and then I write down what are the corresponding Gibbs ensembles. So in our case, you know, it will be that formula, and you can see that I have now many parameters. I have the parameter P, which is a pressure, is scalar, which is positive, but then there's a whole function, which is this confining potential. Okay, and of course you can think of simple examples, but if you want to do hydrodynamics, you better take, you know, a general function. All right. So now comes sort of a slide which sort of, I guess, more for audience like here. I mean, you know, what we want to know. I mean, you know, you might want to first know about something about these measures. You know, sort of, do they have exponential mixing? Do they exist? And so, you know, these are things which one can say something, and people are working on this, so maybe I can say more. But what I want to do for the hydrodynamics, actually, I'm actually sort of already happy with just computing the free energy. So all what I want to do is I want just to do the integral over that object. Okay. So let's be more modest. But now I want to come to a central point, because you know, we sort of now do sort of a little bit sort of a switch of perspective. You see, I mean, the free energy by itself is, of course, no good. I mean, you know, what I want to have, as I emphasized for the hydrodynamics, I just want to have the average of the conserved fields. And now this quantity I would to put in a new perspective. And the new perspective is that, you know, we have this beautiful Lax matrix. Here's the Lax matrix. But now we also have a measure. Remember that, you know, we have now this weighted sort of a priori measure. So this matrix becomes a random matrix. Okay. And so if you think about random matrices, the most natural quantity to study in the large n limit is their density of states, right? I mean, so, you know, the quantity which you want to study is a rather simple object. Namely, you know, you just normalize everything to 1. I mean, you just sort of put at every point, you know, on the V line where you have an eigenvalue, you put a little delta and you normalize to 1. And it's this measure here, which is sort of positive and normalized. It's called, you know, the density of states, typically in the literature. And that's, of course, a fluctuating quantity, because, you know, the lambdas are fluctuating. But in contrast to the lambdas, the claim is, you know, that the density of states, you know, is sort of a rather smooth function. You know, if I change a little bit parameters or take a slightly different statistics, I mean, then the density of states will not change so dramatically. So the assertion is that the real quantity which we want to think of is the density of state, and that density of state in the large n limit will go to a limiting, you know, reasonably smooth function, which I call here rho q. Q sort of stands for conserved quantity, right? I mean, so rather than thinking of the conserved quantity sort of, you know, L to the n, I mean, powers of the Lax matrix, it's much better to think of them in terms of this density of states. And then, you know, the averages I've been talking about are simply, I mean, just, you know, you simply insert this over here, just nothing else but the moments of this particular measure, right? I mean, so that's a very useful thing to have. Rather than thinking about the moments, it's much better to think about, you know, the probability density itself. And so this is this whole Q. Okay, so this has, you know, in the limit, I mean, it has small fluctuations, and then we'll go to something which is deterministic. So now the picture of the hydrodynamics, it becomes sort of rather clear. You see what you think is, so let's imagine that you have evolved your Toda that is for a particular time, and then you start freezing, and you look at the little box, and then you look at a little box, let's say, of something like 300 particles. What you should do mathematically, you know, you cannot see the conserved quantities. Rather, what you should do is you form the 300 by 300 matrix, and you look at its density of state. And the claim is that this density of state is something which is varying slowly in time. If I look at the neighboring box, I will see something which has almost the same density of states. If I'm going to look at some later time, I will see another density of states, which is not too far the one which I will have time t equals 0. And it's the density of states, which eventually will be governed by a hydrodynamic equation. Okay, so this is a very central object of the whole thing. Okay. All right, now we have to work a little bit to get some information. That comes later. And now I want to do this integral. Now you're stuck. You see, it's a very complicated integral. I mean, I have no idea how to do that. Okay, I have to show you the integral now. Sorry. Anyway, so here it comes. Okay, so now we want to do this integral. But now there's a very beautiful theorem by Dumitru and Edelman, who were not thinking about Toda at all. I mean, they were thinking about other things. And they proved an identity. And the identity looks the following. I mean, they look the same as the Lax matrix. You know, they cut off this little matrix element over here, but this will not change the free energy. I mean, that's just a small change. And so you know, in spirit, that's just exactly the same matrix. I put here the B's instead of the momenta along the diagonal, just to emphasize that, you know, the theorem has nothing to do with the Toda lattice. It's just an abstract theorem about tridiagonal matrices. Okay. And now what they prove is the following identity. Well, okay, no, let me say this one by one. Okay, they never looked at this particular partition function. So you look at this particular partition function, which is not exactly, well, I'll come to this, but it's sort of the same. But then what they say is that, in fact, what they can do is, you know, under this measure here, they can compute what is the distribution of eigenvalues of this matrix. You see, that's of course very important, because if I would tell you the distribution of eigenvalues, then of course you know how to compute this thing. And this is what is written here in the next paragraph. You see what happens under this mapping, or sort of under the identity of Dumitru and Edelman, if you do this extra term here, this extra term is just you know, just linear in this potential. I mean, so if you do the spectral representation, it's just linear in these eigenvalues, right? I mean, so this goes simply, the sum is just here the trace, and so this becomes a very simple term. And what they tell you is that, you know, associated with writing down the full distribution of the eigenvalues of this random matrix is a particular volume element, and that volume element turns out to be the sum over the logarithm. And that's sort of, you know, a very famous object in statistical mechanics in one dimension. This is the so-called log gas, because these eigenvalues sort of look like a gas which has a logarithmic interaction. Okay, and so the amazing thing is that you know, the formula which we want to do, actually after sort of somewhat tricky transformation, turns out to be something which is first of all well known and well studied, and on which we can actually make progress. But you see, life is not as good as I told you, because, you know, the theorem actually holds for any beta. But when you look at this formula here, before we had here a fixed number p, and now it's linear invariant. So actually, we have a linear ramp of the pressure, and that's nice enough. But that's not what we need. You see, we want to have actually the pressure sitting there. We don't want to have something which is linear invariant. And so now I can sort of, you know, make a clever choice of the beta. And then we can sort of, you know, get sort of, how do you say this? We can sort of catch two flies with one stroke. Namely, I want to pick the beta as 2p over n. That's one particular choice. Then you see that this is sort of slowly varying in the sense that, you know, this has now a slope 1 over n. And then when I look locally at this measure, it will be just sort of like a constant value. So we really have the one which, we really have the Toda case. And on top of this, the beta stands in front of this logarithmic interaction. And now this is a 1 over n. And therefore, you know, this interaction becomes of mean field type. It's a 1 over n of the thing. And that, of course, simplifies the statistical mechanics analysis. And so at the end of the day, if I compute this partition function in the limit as n goes to infinity, then this first assertion is that because of this linear ramping, it's an integral over the Toda free energy at this particular pressure with the same confining potential. And for this quantity, there will be a variational problem. And so let me show you the variation problem. So, well, maybe I can, you see the variation problem you can see from here. This just is linear in the density of states, and that's quadratic in the density of states. And so, you know, you do the obvious limit. I mean, all these things have been studied in great detail. And so the free energy function is, that comes from the confining potential. This comes from the logarithmic interaction. And this one is the usual entropy. And one can prove that it actually has a unique minimizer, which I call rho star. And if I do this unique minimizer, then the assertion is that I can evaluate the mean field energy at rho star. But remember that we still had, you know, this integral and the p. And actually, if you want to get the true Toda free energy, the generalized free energy as a function of the momentum and the v, then I have to do this funny derivative with respect to pressure. And then you get this identity. This is sort of the correct free energy of the Toda lattice. So you see, we have made one little step in our program, namely what we have achieved is that, you know, in some sense, we have sort of a constructive formula of how to compute this this generalized free energy. People who know about integrable systems should not be surprised. You see, if you go back in literature, I mean, there's the famous Yang paper in the 50s, I mean, who studied the delta Bose gas, and one of their big contributions was that, well, LUD actually first studied it for zero temperatures, and that was sort of the very first in understanding this. And then Yang said, well, why don't we do the thermal case? And you know, of course, there's some jumping, and you have sort of these beta equations, and it's much less clear than in our case. But what they came up with is exactly a free energy function, very much of this type as over here. It's of course not identical, but it has a very similar thing. I mean, this log here is not the log. It's a function like 1 over 1 plus x squared. So you know, w minus w prime squared. So it's a different function, but. And then, of course, you know, this is the classical case. So in the quantum case, you have here the Fermi potential. So it's rho of omega log rho of omega plus 1 minus rho, etc. Anyway, so there are differences. But the main point is that the fact that there is a variational principle is not so surprising. Okay, so now I have a little bit of time, not too much, but a little bit of time. And so I want to sort of, you see, it's slide 11a, which means that I made it especially for this audience because I thought, you know, in this audience, you might appreciate the next step, because you see, I emphasized for the beginning that we want to say something about the average current. So here, it's again, you know, just a definition. I mean, I take the time change of the local conserved quantity, that is Ij, and that must be of difference type. That's sort of what I mean. And these are some functions. And in fact, you can write down what they are. I mean, you find that you know, there's given still sort of like the JJ matrix element of the Lax matrix to the power n, because I'm looking at the n's conserved current. And then, you know, the L down is just the lower triangular part of the L matrix. And so it's something like this. But now you see this formula, and now you see that I'm completely stuck. Why am I stuck? Because you know, this matrix element will, if I do the sum here, you know, it will depend on the eigenvectors. It will not just depend on the eigenvalues. And so the formula which I had is totally useless. I mean, it just doesn't. I try to think about the eigenvectors, and it just goes nowhere. And when you look at, you know, sort of in the recent history of the subject, of course, people were not so completely clear about this hydrodynamic picture and all these kind of things. But the main technical stumbling block was that they had no idea how to compute the currents. See, the fact with this free energy and such kind of things, they were sort of known in many models, and you know, they're sort of taken to more or less for granted. How to compute the currents, and it was an absolutely big riddle. And the big sort of, you know, sort of step forward in this subject is that when in 2016, 17, in particular models, you know, people realized how to guess what the correct current is, and then you know, they somehow guess what the current is in others, and then there many work to sort of try to sort of emphasize. Now, I looked at this literature, and of course, you know, there are sort of beautiful guesses, but when you really ask, you know, what do they show? I mean, then you know, it's not so completely clear. And so at some stage, I was working on this, and at some point I came up with another identity, which I want to explain you, which is based actually on two inputs. But let me first explain you what the identity is. So the claim is that yes, indeed, for large n, I can compute the expected value of this current. So these are these particular objects, which I have to average at, let's say, current at site 0 in the GG. Okay. And the surprising formula is that it's related to the fluctuations of the eigenvalues of this mean field log S. You see, the eigenvalues go to a deterministic limit, but then relative to this limit, you have Gaussian fluctuations, which are, because we're doing the mean field there, of order 1 over square root of n, right? I mean, it's just standard fluctuation theory, and this fluctuation theory has a particular covariance. So here's one sum function, here's another sum function, and the assertion is that this covariance is actually given in the large n limit with the proper truncation of this covariance. Okay, now I cannot really explain, where this function comes from, but I want to explain one thing. The n, of course, reappears over here. So if I look at the nth moment, if I look at the nth order carbon, then I have to put here this to the power n. So that's fine. Now, why do I have here power 1? Well, the power 1 comes because there's a very special current, namely the zeroth order current, which I showed you already. It's just a pj plus, it's just a pj actually. That is also by itself conserved. I mean, it's just minus of the first conserved field. So that just means that, if I take the density, then the current is the momentum, but the momentum itself is conserved. That's a very unusual quantity. If you look at any other conserved fields, that's not the case. I mean, if I look at the energy current, then of course the energy current is not conserved. In many models, there is such kind of observable which has this property, but for the Fermi-Hubbard model, it's not true. And then there, this kind of technique doesn't work anyway. And it's based actually on a symmetry which people sort of knew, but they didn't realize it in this connection, which is sort of the charge current matrix. But this goes maybe too much into details. I just want to tell you that once I have this formula, then I can turn the crank, so to speak, and I can actually upturn the limit, and then I get the kind of things which I promised, namely then I get the average function, the average currents as a functional of the average conserved quantities. Okay, so now I'm sort of closing up already, yes, so I'm closing up already, so I want to do a slight summary, but since I had not said anything about the hydrodynamic equations, I want to use the last 5 minutes to talk about these equations and tell you a little bit. I mean, I want to give you a feeling what the final result or the final conjecture is. Okay, so here is on a large scale my space-time picture. It's in one dimension, and here is sort of a little space-time cell. Let's say a space-time patch at time xt. Now the assertion is local equilibrium. So the statistics of these particles will be given by one particular GGE, which is an infinite set of parameters. And the good parameters are what I call the stretch. I mean, the distance between neighboring particles, of course, at the point xt, and at the end, the other parameters is the mean value of the conserved charges, right? So that's what I call rho q, and now it becomes also xt dependent. Okay, so your hydrodynamic evolution equation will be, of course, space-time, and then they are, have a full function, which is sort of here, which has an argument w. So in the usual case, it would be just a discrete set like 1, 2, 3. Here is now in the continuum. And of course, what I mean is that these are the CG parameters, but what I see locally is here a generalized Gibbs ensemble with these particular parameters. And then the claim is that these parameters sort of evolve in time. And of course, you have microscopically conservation law. So on this hyperbolic time scale, in the limit, this will go over to a coupled set of hyperbolic conservation laws. So I've written them down here. This one is the first one, which is sort of the obvious one. It's just a continuity equation. Okay, and of course the Q1, I mentioned this already, that's just the first moment of rho Q. So this is how this equation sort of couples into the rho Q. And now you get a conservation law for function, which depends also on W. So it's like in kinetic theory, where you have a particle on one particle phase space and a function on one particle phase space. So that's the same thing. This is, so to speak, living on some sort of one particle phase space. And of course, it's of conservation type. And here you have some more complicated object, which is this promised functional of nu and q. These are our basic variables, right? Okay, and now I tell you a little bit, I don't really go into too much detail, but I mean, just to give you an idea. So you first define this linear operator, which uses this logarithm simply as an integral kernel. And so it's obviously a symmetric operator. And you also define some slightly different functions. So these are all functions. So that's just defining this particular function rho mu, which is rho q divided by this function. Okay. And then the assertion is that this whole expression can be written in terms of the rho mu and can be written in terms of acting with the inverse. So in some sense, inverse, I mean, okay, with this particular inverse of this operator on the linear function. So this theta is here just a linear function. Okay. So if you want to know what this is, you see, you have to somehow invert this operator. Numerically, this is actually doable. And, you know, I mean, this seems to be sort of a rather well-behaved object. The numerics, you typically go to normal form, and there are other schemes, but you know, there's plenty of experience of how to solve numerically this kind of evolution equation. I don't think there's any mathematical theorem which tells you that such kind of, you know, I mean, I think people just don't know about solution spaces and all these kind of things. I mean, this is not what they think about. I mean, so, but in terms of actually, you know, sort of on a numerical scheme handling this equation, I mean, you know, they seem to be rather well behaved. And for instance, you know, these experiments on the delta Bose gas, where they sort of want to compare, you know, the solution of the hydrodynamic equation with what you observe in the experiment. You know, I mean, there they use sort of a particular numerical scheme to solve the hydrodynamic equation. And that sort of seems, at least for the purposes they use, sort of seems to be sort of reasonably effective. Okay, so let me sort of go to the outlook and to the summary. So if you want to know really more about Toda, and then maybe, you know, some of the things which I could not explain because of the lack of time. I mean, there are sort of somewhat lengthy lecture notes which you can find on the archive. I mean, of course, there are sort of many pages on Toda, but you will find also something on quantum Toda. There will be the deep linear. And one thing which I've tried to emphasize in this lecture notes is sort of, you know, the similarity between the hydrodynamics of various integrable models. I mean, that's sort of one of, I mean, to me, still amazing feature that you know, I mean, once you're on the hydrodynamic scale, I mean, things look actually very, very similar. So if you really want to know, I mean, you know, the first thing I really would advertise are lectures by Benjamin Doyon, which are a little bit earlier. He also talks about Toda, but he talks also about the quantum cases. I mean, they are simply, you know, more readable, and he gives more explanations and sort of more pedagogical than what I've written up here. And then if you want to know more, really more, there is a sort of volume of Journal of Statistical Mechanics on emergent hydrodynamics and sort of lots of articles. I mean, anyway. So I emphasized already the universality. I mean, that's something which I still find amazing. What is left over on the macroscopic scale is, of course, you remember whether the original model was quantum or classical. And the other important dynamical thing which you remember is the two-particle scattering shift. I mean, that is supposed classically and quantum mechanically. It's in our case, it's this logarithm. This logarithm is the shift, the scattering shift when you solve the two-particle problem. When you go to the Lieb linear, then you have to take two Lieb linear bosons and compute their scattering. It's that scattering which still appears in the hydrodynamic equations. And besides all these things, another important development is that, I mean, once you have Euler, you presumably imagine that you could sort of do a density, a gradient expansion, and indeed you can. And then there is actually a Navier-Stokes correction, and one knows, I mean, in some sense, fairly explicitly what this Navier-Stokes correction is. So thank you for listening.
Thank you, Herbert. Are there any questions?
Yes, I'm happy to answer questions. Yes.
Either locally or from the remote participants.
Non-discrete, right? Is that the question? Sorry, I don't know who asked the question, but I mean,
yeah, I don't know. Where is the microphone? Because I think Herbert cannot. We have some sound problems here because it's very loud because of a storm outside.
I see. Okay. No, I'm not muted. I mean, so can you hear me?
Yes,
we can hear you.
All right. Okay. So I understood that the question is, what about continuum integrable system? Is that right? Or That's a good question, but I don't know where this question was asked.
Answer the question. Sounds good.
Answer the question. Okay. So this is a very personal answer, but since I know that some people are interested in these things, let me tell you. So the main difficulty. So let's take nonlinear Schrödinger equation in one dimension, which is integrable. Okay. Now you want to write down the generalized Gibbs ensembles. Now, of course, yesterday we heard, there's all this beautiful work about Gibbs meshes for the NLS. But this is not enough. We want to do the generalized one. So rather than just having the L squared in top, we want to have some general function. And so when you look at the higher orders, conserved quantities, which of course you can find in the literature, you can write down, then you see that you get higher and higher derivatives of the field. And then to me, even the program of writing down these generalized Gibbs ensembles looks so difficult that I don't want to even touch it. You see, it's a very singular, I mean, the lowest order is sort of, you just have the quadratic part, and then you can barely sort of define what you mean. But then if you go to the next order, well, presumably to have a stable system, maybe you should take order 3 and order 4. But, I mean, then I think, I mean, to me, it would look like a miracle if you could do it, okay? And so my philosophy is actually sort of slightly different now. But what I am doing is that there is this amazing point that, for seemingly for every known sort of integrable continuum model, there is a discretized model which is also still integrable. You see, if you naively discretize, of course, you will lose integrability. Now, for the nonlinear Schrödinger equations, it's the Ablowitz Lattice equation, which is a discretization, which, as they showed many years back, is actually integrable. So if you want to do such kind of a program, the natural object to look at is the Ablowitz Lattice. That, you might try to analyze. Now, I'm not reporting any, exciting results here. I just want to say that it looks to me, if you want to sort of do this kind of program, you somehow are forced, in order to have this generalized Gibbs ensembles, you're somehow forced to look at the lattice, and that's not so bad news, because even if I'm on a lattice, I mean, you have an integrable version. Of course, you can do other models. I mean, like the Carloccio-Sutherland model. These are particles in the continuum with a two-pair interaction, like the 1/sinh squared potential. Of course, for them, I mean, you should in principle do the same thing as you can do for the Toda lattice. But I go to the books of Carloccio. Of course, there's a lax matrix. All these things are existing. But then the next step, I mean, sort of where I use this Dimitrov-Edelman theorem, I'm completely stuck. I mean, I can write down all these objects, but then when you ask, what can I say about the density of states of the lax matrix in the Carloccio-Sutherland model, then or Carloccio-Moser model, then I don't know how to proceed, right? I mean, so there are lots of sort of potential barriers which you have to climb. But the idea is that if you want to do a classical model, I mean, to do the straightforward continuum sort of doesn't look so nice. Of course, you see also quantum mechanics, you have this problem. If you ask, maybe some people are interested in this kind of philosophy. So if you want to know, I take the Lieb-Liniger model, which people presumably know. I mean, so that's just the delta Bose gas quantum mechanically. Now you look at the conserved quantities. Well, of course, you have the energy. That's it's just like in our case, just the sum over lambda j squared of the solution of the beta equations. Now you say, okay, what about the next order? Well, of course, it's clear. I mean, it's just the sum lambda j to the power 3, and then I look at the fourth order. It's a summation over j lambda to the power lambda j to the power 4. That's fine. That's a well-defined operator. You have the full spectral representation, and there it is. Okay, so you can write it out. But you see, what you cannot check is whether this operator, whether actually it defines a local, whether it's actually a local conservation bound. Then people are writing down carbons. I mean, these are totally undefined things. I mean, I don't know how to deal with them. So my conclusion is that if you want to do, I mean, it's fine what they do, but my conclusion is that if you want to be a little bit more, sort of a little bit more on the more mathematical side, it's a very good idea to actually start from a lattice model, you know, like XXC is a perfect model, for instance, right? I mean, just, you know, where all the basic objects on which you want to say something are already well defined. Okay, so this was an answer which was too long, but anyway.
Thank you, Herbert. Other questions? The remote participants I do not see, so if you want to ask a question, just speak up, please. Yeah, if so, I don't see any question at the moment, so I would suggest we thank Herbert again. And coffee break until 4:30, right?
Breakout rooms for the online participants.
Breakout rooms for the online participants. No coffee for you.